So special thanks to the organizers for inviting me to speak here. This is my first time at the IHES, and it's really a very nice place. And since this is a celebration of the mathematical contributions of Emmanuel, I was thinking about what to speak about, and so I chose a topic from among my projects that I thought might be most closely related to things you've been working on. In fact, this particular project, it's from a few years ago. It's not brand new, but it was very much inspired by work you've done, especially early work, Galois, the equidistribution of Galois orbits for torsion points on abelian varieties, the resolution of the Bogomolov conjecture. Of course, it seems equidistribution has been a theme in your work over the years. But also more recently, some writing you've done on the Zilber and Pink conjectures and their formalism. So I was reading through some of the things you've written as I was preparing what to talk about. So it got me thinking about the analogs of this Zilber and Pink conjectures and formalism in the dynamical setting. And more or less everything breaks down in a dynamical setting, but anyways, it's still inspiring and there are interesting questions that we can ask. And so what I'm planning to do is talk about a project which is about elliptic surfaces. But as I go through and describe the project, I want to describe also some questions, some open questions on the dynamical side that we really don't know how to answer, but we're inspired by what's known in the setting of abelian varieties or families of elliptic curves. Okay, so that's my plan. This is the project I'm talking about is a joint project with Mirto Mavraki. However, during the last hour, as I was listening to Philip's talk and admiring his beautiful hand-drawn Julia set, I was thinking that actually his talk is much more dynamical than my talk, but I couldn't resist adding one slide to my lecture here. So just before I begin my talk, this is a picture for his talk. This is the Mandelbrot set, so it's the family of quadratic unicritical polynomials, and the examples that his theorem applies to in degree 2 are all of the yellow dots. So I just wanted to illustrate, because there were questions about, how many polynomials are there that satisfy the hypotheses, and this picture is showing all of these examples in degree 2, and you can't tell, but the yellow dot, there are infinitely many yellow dots, and they accumulate everywhere on the boundary of the Mandelbrot set, and they're what we call these hyperbolic centers. So there's one in each of the connected components of the interior of the Mandelbrot set. So anyways, this is not about my talk at all. I just thought you might appreciate seeing a computer-generated image of some of the things that Philip was talking about. Anyways, okay, back to my talk. All right, so the setting for my talk, now, what time is it? Okay, I'll go on and on about things that are unrelated to my talk. Okay, so the setting here is elliptic surface. So the standing assumption for my talk will be that, so this is a family of elliptic curves over some base curve, which is not isotrivial. Okay, so the tori are genuinely varying, their complex structure. I'm assuming that the base is projective, so I didn't draw it, but there are some fibers where these elliptic curves become, they're not elliptic curves, they're singular fibers. Okay, so the picture is not quite as I've drawn it. There will be some finitely many points in the base over which the fiber is singular. I'm assuming that this projective surface and all this data is defined over a number field, because I will be talking about some arithmetic features of this picture. All right, so I'm interested in properties of height functions in this setting. So there are two height functions that one can consider. There's a geometric height, and then there's the arithmetic height. Now, this elliptic surface of course, can be viewed as just one elliptic curve when defined over the function field of the base. So here, if little k denotes the function field of my base curve, then, of course, the rational points of that elliptic curve correspond to the holomorphic sections of this elliptic surface. But also, over each of the points in the base that are, say, q bar points of the base, if the fiber is smooth, then you have the sort of sorry, I didn't even mention the height in the geometric case. So in each case, we have the Néron-Tate canonical height for this elliptic curve. So these are the heights that I'm interested in. I didn't give a definition, though I've written some basic properties. So we have the geometric height associated to how the geometry of these sections grows under taking powers on the elliptic curve, is what it's reflecting. And then we have the arithmetic height on each of the smooth fibers. Okay. And some basic facts that I've written here about the heights. Again, I didn't give definitions, but some important facts are that the height, is a real valued function on the points, and it's non-negative, real valued function. And the zeros, as we saw, for example, in Philip's talk, in the setting of the Weil height or the dynamical heights, in this case, the zeros for a point of the elliptic curve are just the torsion points. Okay? Remember that I'm assuming that E is not isotrivial, so that's why this also holds in the geometric setting. Okay. All right, so before I formulate the problem or the questions that I've been thinking about, I said I'm going to describe some questions and problems in the parallel dynamical setting. So just for a moment, let me just say what that parallel dynamical setting is that I think a lot about. So this picture here, which I'm thinking of as a family of elliptic curves, gives rise to a family of dynamical systems. So you can take, for example, an endomorphism on each of these elliptic curves. For example, multiplication by 2 map on each of these fibers, or you can think of it as a rational map on the entire surface, gives rise to a family of maps on projective spaces, in fact, in 2 different ways.
So you never consider dynamics on the base?
No. So the dynamics will be the identity on the base. Yeah, and often these bases, of course, don't even have interesting dynamical systems, especially if it's a curve of genus bigger than 1. So, so here I'm thinking of, yes, the dynamics on the fiber, and so this gives rise to what we think of as families of dynamical systems, in this case on P1. So for example, we could take a degree 2 quotient of each of these fibers and get a P1. And the multiplication by 2 map on each of the fibers gives rise to a family of functions on P1 of rational maps, they're rational functions of degree 4 in this case, on P1, parameterized by this base. But of course, again, remember that some of the fibers are singular, so the corresponding quotient would also be singular in the sense that it's not a rational function of degree 4, and the induced map on the total surface will have some indeterminacy. But so we can ignore those. But just as a family, at least after excluding finitely many parameters, you get some holomorphic family of maps. Alternatively, in this case, in fact, we could actually, rather than taking this quotient, we could embed this family of elliptic curves as a family of morphisms on a higher dimensional projective space. In fact, you can do this just in P2 in this case. You can have a family of maps on P2 where this multiplication by 2 map, if you choose your embedding well, your multiplication by 2 map will extend to a morphism on a projective space. And in fact, you can do the same with families of abelian varieties. You can take a family, whichever family of abelian varieties, choose an endomorphism that, for example, take an endomorphism like multiplication by 2, and you cannot do the quotient to get a family on projective spaces, but you can always do the embedding. And one of the features here is that the torsion points, and this becomes relevant, but the torsion points of the elliptic curve correspond to the finite orbit or pre-periodic points of the dynamical system, related to what Philip was mentioning and the parallels of the heights. In fact, the height, so he mentioned the Call-Silverman canonical heights, and I'm glad he did, because I'm not giving you a definition, I'm just mentioning that they exist. So just as in the setting here where you have, say, a geometric height for the elliptic curve as one elliptic curve viewed over a function field, or the arithmetic heights as a family of heights, one for in each fiber, you have the same for the dynamical systems. There are these analogous canonical heights introduced by Call and Silverman in the 1990s, which reflect complexity, arithmetic complexity along orbits, and growth of that complexity along orbits. And similarly, you have an arithmetic height on each of the fibers at which you have at each of these fibers, where let's say we have good reduction, and then the corresponding geometric height, viewing it as one map over a function field. And, I wrote it for P1, but this makes sense also for Pn. And similarly, this is what I was saying, that height 0 for the dynamical height corresponds to pre-periodic. Okay. Of course, in the case of well, I'm going to ignore that point right now. All right, so going back to the elliptic curves. This was just to keep in mind how I'm thinking of the family of elliptic curves as a special case of a family of dynamical systems. So when I start formulating questions later, it'll be clear that really anything that one can say about this picture is something that one could ask about a more general class of dynamical systems.
So there is some non-triviality assumption. I mean, if you have a constant family of endomorphisms, so this is probably correspond to the isotrivial part.
That's right. Right. Certainly this will fail. This geometric thing here will fail if it's a constant family. The same as it would in the setting of elliptic curves and abelian varieties. Yeah. But I'm just going to ignore that point because I'm not really going to talk about the more generally. But let's assume that everything's not isotrivial. In dimension 1, that's already enough. Okay. All right. So going back to this setting, as I said, I have this elliptic surface defined over a number field, and I said that the rational points, the geometric rational points, correspond to sections. Now, the story, the project that we were working on begins with the following observation due to Tate, which was a connection between these two different heights. So explicitly, what he showed was that if you take one of these sections, such as what I've drawn here in green, and you look at the arithmetic height along the points of that section, that really gives you a height on the base curve. A height in the sense that it's related to sort of a standard Weil height with respect to some embedding of the curve into a projective space up to a bounded correction. Up to a bounded correction. So more precisely, let me just read what it says here. For any such section, so rational point, there is in fact a Q divisor, call it dp, which lives on the base. So with respect to which you construct the corresponding Weil height. The degree of that divisor is the geometric height of this point, and the two heights are comparable. Again, the arithmetic height along this section compared to some sort of reference height on the base, up to a bounded correction. Okay, and so one of the first things that Mirto and I were looking at, now this was already some years ago, was to understand properties of this as a height function. Notice, of course, this is not defined when the fiber is singular. Right? This is only defined away from finitely many points t in the base. Of course, this is defined everywhere. But up to bounded correction, you can just assign whatever value you want, and it doesn't matter. You can declare it to be a height function. But we were interested in what exactly happens on those singular fibers. How does the height behave as you approach one of those singular fibers? And one of the things we observed at the time, so this was in a paper that was published in 2020, was that in fact these heights, not only globally but also their local input, behave very nicely across the entire base curve at all places and across the singularities, that is to say. So one can formulate this statement, and I'll mention some references in a moment, but one can formulate this statement as follows. We observe that this function, this height function on the base, again, which is defined away from a finite set of singular fibers, is in fact the height induced from an adelic, continuous, semi-positive, metrized line bundle. So an adelic metrized line bundle in the language that we've learned from Shouwu Zhang, anyways, on the base curve. So as we know, whatever this line bundle is, I mean, it's a Q line bundle really, its degree should be equal to the geometric height. So it was just looking at the fine structure of this height as Tate was looking at it at the time. So to observe this piece, just the fact that it extends nicely across the singularities was building on some work of Silverman. When was that? So also maybe around 1990 or early 1990s, where he was studying properties of the local height functions as you approach a singularity. And he was studying some features of it, and then we realized we could use that to say, you can build a nice metric on your base curve that's actually continuous. And then building upon that, we then observed that we were looking at these line bundles and looking at their intersection numbers. Now this is an arithmetic intersection number. We call it an Arikhelov-Zhang intersection number, which can be computed. There's a definition there. I'm not giving you all the meaning of all the symbols, but there is this arithmetic intersection number which vanishes when the two line bundles equipped with their metrics are actually the same, when they're isomorphic. And one can observe, really once you have this structure, it follows from some work of Masser and Zanyer that you get that this intersection number is 0 if and only if the 2 points were linearly independent. Okay, so in other words, this structure, this metrized line bundle, picks out the algebra of P, of a point. Okay. So it really determines the point up to linear dependence on the elliptic curve. Now, why were we doing this? So, of course, I was just curious initially about the structure of these height functions and what happens near the singularities, and whether or not one can extend. Of course, I was thinking about dynamical systems, and we were really using dynamics initially to prove this statement. But at the time, what we realized was that, these statements that seemed very formal in fact implied, this is just a remark, I actually don't want to spend a lot of time on this slide, but at the time we realized that this gave a Bogomolov-type extension of exactly the theorems we were using of Masser and Zanyer, a statement a Bogomolov-type statement for what? For curves, such as these types of curves, but in abelian varieties that split as products of elliptic curves. So in families of abelian varieties that happen to split as a product, the notation is really, should be a fiber product of a collection of elliptic surfaces. And the statement was that as long as I'm going to state it vaguely, as long as you don't have a special section, then there are only finitely many special points on that section, in this case, small points. And of course, this type of statement, I was saying, was very much inspired by, for example, in the work of Ulmo and the Bogomolov conjecture in the setting of one abelian variety. And here we were looking at families of abelian varieties. Of course, since this theorem, can you even see that? I just realized it's kind of invisible. It's all right? Okay.
The people on the left cannot see the beginning of the world.
Oh, that's too bad. Is it possible for the projector the screen to be shrunk a little? Maybe not. Sorry. All right. I didn't know. I would have made the slides slightly smaller. If I had known that squeeze. Well, anyways, what it says is that for any section of, say, you take a fiber product of a family of these elliptic surfaces over a given base, if you take a non-special section, which I'm not going to define, then there are only finitely many points with small arithmetic height. And we were using this structure to prove this statement. And since that time, I mean, there are a lot of theorems that have been proved in this direction. There's been a lot of development since 2020, in fact, on problems of this sort. And so I won't get into that. But there's a lot of work happening in this direction, as many of you know. Okay. Okay, so let me pause here to observe. The analogs of this statement are definitely not known in the more general setting of families of maps on the projective line. Okay. So what do I mean by that? Let me give some explicit comments on what we don't know. So again, remember here I'm thinking about a family of elliptic curves or a base curve. Replace that with a family of maps on P1 over a base curve. So just one-dimensional, family of one-dimensional dynamical systems, of which this is then a special case, because these quotient to maps on P1. So for example, let's just go back to Tate's theorem. We do not know this in general for families of maps on P1. This is still open. Even the very first part, the first observation in this statement is that there's a Q divisor that I'm calling dp, whose degree happens to be this number. We don't even know that these geometric heights are rational numbers in the more general dynamical case. And actually, so one can prove this, that the fact that this is rational using dynamics, but the family of lattice maps, the maps that you get from studying from elliptic curves, are really very special class of dynamical systems, and they have all sorts of good properties that general dynamical systems, rational functions, don't have. And so the proof breaks down. We just don't have the structure to show that these numbers are rational numbers. And so that's still an open question, whether or not those geometric heights are rational numbers.
So is it expected that they are rational?
I expect that they are, yes. I expect that they are. Now, what makes it more subtle is that it's also the case here that all of the local heights, even working with sort of local completions of the field, the local heights will also be rational because they're computed by intersections for narrow models. That fails in the dynamics. So we know that if you work locally and look at the local height contributions to these, well, a point that's only defined locally doesn't have a global height, but the local heights can be irrational. And so we have criteria that determine when they're irrational and when they're rational. And I've spent some time thinking about this in a project with Dragoš Gioka. But I still believe that the points that are in fact themselves global, so actual genuine rational points, I think those numbers are rational. But we just don't have a structure. We don't have the intersection theory. We don't have the neuron models. We don't have the structure.
And are there computations perhaps showing some evidence?
Yes. So we have some settings and conditions that guarantee it. And there are actually a bunch of computations. Actually, it reminds me, during, I guess, something Francois said during his talk, and that Yunqing mentioned, or even the one that was on the theorem that Philip wrote on the board. There are these algebraization theorems about starting with power series with integer or rational coefficients, and when are they actually rational functions or algebraic functions. There are some approaches to proving that these are rational numbers by studying the types of power series that arise to describe local points that have particularly complicated dynamics. If geometrically they're in a Julia set, then they can have some very complicated dynamics. And we're actually hoping to be able to use some of those algebraization theorems to attack a problem like that. But anyways, right now it's really a wide.
It's very peculiar because in most situations one expects things to be irrational and can't prove them.
And want to prove it's irrational, right? Here I'm trying to prove it's rational and I cannot do it. So it's true. Unfortunately, the arguments by contradiction don't quite work. So of course that's like step one. And then there's all the rest of the steps, which certainly would be nice. But okay, so what? Maybe it's an R divisor. Okay, but we don't know this. So even in the cases where we do know that this is rational and we can build this, we have a candidate Q divisor on the base curve, we don't know this O of 1 condition. It is known in many settings, but not for all maps and all points. So that is also still open. What else? Oh, what did I write here? Yeah, is this a height? Right, so is there really an O of 1 difference here? That we don't know. What else? Are the metrics continuous? So here, we were looking at the structure of how these heights, what happens to the heights, in fact, the local contributions to the heights as you approach the singularities. And we had the help of a series of 3 papers that Joe Silverman had written that was studying some of these, looking at some of these properties. And there's, of course, a lot more work on height functions associated to elliptic curves. There's a lot of tools out there. We just don't have those same tools. So it's known, for example, that you get continuity across the singularities in all cases when the maps are polynomial. There's the theorem of Thomas Gautier and Charles Favre that covers the polynomial maps. But for general rational functions, we don't know that. I will mention, I wrote here in parentheses, even if you sort of write down the candidate for these metrics, they aren't necessarily adelic in the dynamical case. There are lots in the sense that here this metric is given by some standard model metric at all but finitely many places. And that fails in this general dynamical setting, where you can build examples of a family of maps and a section where the metrics are necessarily non-trivial or interesting at all primes. It can be defined over Q, and you can set them up so that they have some interesting non-trivial metrics at all primes. So they're not adelic in the sense that we usually think of the word adelic. Anyway, so I think there's some interesting questions there about degenerations in these classes of maps, and we don't know how to answer these questions. We just don't have the structure. Of course, even if you have all that structure, one I had to throw this in as well. The final thing was, suppose you have all this structure. To what extent does this metrized line bundle determine the point or the orbit of the point? The analog of this linear dependence condition would be an orbit relation condition. Does having that same metric determine some relation between the points? And that's known, again, in many settings. For example, in the case of polynomial maps, it was also covered by some work of Thomas and Charles Favre, but we don't know it in general. So these are some questions that remain open. Okay, moving back to the elliptic surface. Okay, so where did we go from here? So, okay, we couldn't do a dynamical version, but we decided to study a little more closely the intersection numbers themselves. The computation and the numbers are a little bit mysterious. We know some general properties. One can usually work with a list of properties that these line bundles and their intersection numbers satisfy, but it's hard to really get your hands and actually compute some of these things. This is a definition. These are, and again, I'm not expecting you to get much from what I've written here. These are the local height contributions, the curvature associated to this line bundle. Anyways, there's a definition. But what properties does it satisfy? So Mirto and I were looking at features of this number as you vary the points P and Q, as you consider all rational points on a given elliptic curve over a function field like this. Okay, so what were we able to prove? Here's the main theorem that we proved in, now this is now in a paper that was published a few years later. Anyways, it came out a few years ago, but the theorem was the following. So again, in the setting that we were looking at, I have this non-isotrivial elliptic surface defined over a number field. What we observed was that as you look at all the pairs of rational points over this function field, these intersection numbers behave like a geometric object. Okay, so these are arithmetic intersection numbers, keep in mind. This is data from working with these as sections defined over a number field. And it turns out that these numbers are actually comparable in size to what we call the Néron-Tate geometric regulator. So this is just a thing defined in terms of the geometric height. This is the inner product, the height, the Néron-Tate inner product on this E of k or E of k tensor Q, if you think of it as a vector space. And then this is the usual Néron-Tate. And this quantity here, I should mention, actually, maybe I put that on the next slide. Yeah, okay. So this quantity here, okay, so this is something about the elliptic curve over the function field. And it's known, it's well known that the height, the geometric height, of course, is a non-degenerate quadratic, defines a non-degenerate quadratic form when you tensor with R, thinking of it as a real vector space. And this quantity here is biquadratic. If you fix P, it's a quadratic form in Q. You fix Q, it's a quadratic form in P. It's biquadratic. And it's known that it has the same non-degeneracy properties. That is to say that this vanishes only if the two vectors are linearly dependent over R now. Okay, over R. All right, so this was known. So, and by the way, one can just, for general, we can look at sort of general features of these intersection numbers. They're not, it's not linear in P and Q. It turns out that this thing is quadratic in the same sense that the height is quadratic in P and Q. So we also think of it as a biquadratic form. And this inequality turns out to be easy. It's very formal. It's just studying general properties of these intersection numbers and their quadratic nature. But this was the interesting part for us. Now, I'll tell you why it was interesting in just a second, but let me just emphasize that what we really wanted to know was whether or not these intersection numbers also give us some non-degenerate biquadratic form. It was a way to compare, so the intersection number, and so similar to if you're familiar with, say, Silverman's specialization theorem, when looking in families of elliptic curves, or abelian varieties even, and taking a section, you know that the height along that section will grow as the height of the parameter grows at a rate that's related to the geometric height. In other words, the geometric height governs growth of height along sections, whereas these intersection numbers govern small height features along these sections. So this inequality, our goal was to understand, we know that this governs sort of small height behavior along a section. This we know governs large height behavior along sections. But can you also control small height behavior geometrically, I guess, was what we were trying to understand, is one way to put it. Now, on the next slide, I want to show you, okay, so this is the way we thought of it. This is the input of how we proved it. But this slide shows an equivalent, a logically equivalent formulation, which looks much more complicated, but was connected to things that a few people in this room have thought about, specifically the Pink and Zilber conjectures, and a lot of work related to unlikely intersections in this setting of elliptic surfaces, or abelian varieties that split, in this case, say, as a power of an elliptic surface. So that statement, okay, sorry, there's a lot of words on that theorem. So let me, I'll come back to this slide. Let me just tell you the down-to-earth version first, and then I'll remove that and show you the technical statement. Okay, so just so you know what you're about to read. So the down-to-earth version, so it turns out this is logically equivalent to observing the following type of statement. If you're given, say, m sections of your surface, independent rational points over the function field, then viewing them as sections, there are only finitely many parameters where they satisfy at least two independent linear relations on the fibers. There are always infinitely many parameters where they'll satisfy some relation, where the rank of the corresponding matrix that you can build out of these vectors, where the rank will drop. There are always infinitely many parameters where the rank drops, but it's saying the rank drops by 2, so where they satisfy at least 2 independent linear relations, there are only finitely many. Now that was proved already in a paper that appeared in 2016 of Barroero and Capuano. But what we were doing was, as before, a Bogomolov-type extension of this statement. Okay? So when can a collection of independent points satisfy at least 2 relations or come epsilon close to satisfying 2 relations? Let me go. Okay, so this was the informal. I mean, it's still a form. I mean, there's a way to say it, but I didn't define what this is. There's a formal way to say what it means. Here's just some language. This is the way we formulate it in the paper, so I just copied it and put it here. I have a non-isotrivial elliptic surface defined over a number field. Let's say you take a curve in the fiber power over the base, so like a section of the fiber of some fiber power. And then you look at the collection of all flat subgroup schemes inside this space of codimension at least 2. That corresponds to at least 2 relations between points in this fiber power. And then the statement is that if you look at an epsilon tube around this EM2, so that's what this is defining. This is some epsilon neighborhood around this union of codimension 2 things, that curve will only hit this tube finitely often, unless it's contained in it. I mean, unless it's contained in EM1. That is to say, unless it's contained in a union of flat subgroup schemes of codimension 1. Okay, so that's a technical statement, but there were a lot of cases of this that were known, and so our goal was producing this sort of Bogomolov-type improvement of, in this case, a theorem of Barroero and Capuano, which itself was building on theorems of Masser and Zanier, and there were some cases that were already known. In the isotrivial setting, it was already known, and the theorem that I had mentioned earlier happened to cover, was the Bogomolov extension of intersections with the torsion part. So there were cases that were known. But this type of statement sort of fit into the setting of the Pink and Zilber conjectures, but sort of souped up with the Bogomolov bit and the height functions. Okay, but anyway, so this, as I said, so this logical equivalence that I'm saying, I mean, most of it is formal and just some linear algebra to compare this to this, but there is a little bit of input that one needs to know. So we do use the Silverman specialization to bound the height of where those relations can take place. I suppose one should also use Zhang's inequalities for comparing these intersection numbers to points of small height, etc. So there is some input here, but that part was fairly formal. So we were interested in improving this statement. Again, to relate arithmetic intersection numbers to some geometric information. All right. Now, let me pause there to say this type of statement does not have an analog, not a direct analog anyways, in the dynamical context. Okay? There's something very special about families of elliptic curves here, or abelian varieties if you wanted to formulate a version in higher dimensions that we didn't do, but we don't have this type of structure. You can certainly define these intersection numbers in the dynamical setting, where again, by dynamical, I mean families of maps on the projective line parametrized by a curve B. We don't have this object. There is no corresponding regulator. There's no linear algebra. There's no inner product. There's not a vector. We don't even know where to begin with this discussion. So this statement just doesn't have an analog. Okay? However, of course, this type of statement, if you formulate it in terms of that informal version I gave you earlier about having these relations along particular fibers, extra relations on particular fibers, that does have analogs. in the dynamical context. For example, here, let me just, I do have on the slide, sorry, my slides are getting very busy because I'm putting a bunch of things on top of each other, but here's a question that one could ask in the dynamical case. So this is just a direct analog of the theorem that Barroero and Capuano proved. So I know you can't see it on the side, but I will read it out loud. So given a family of maps, F, and let's say you have M points in the projective line, one that you're marking, thinking of them as sections of your B cross P1 over the base, B. So given M points, so geometric points, how often, at how many parameters can they satisfy at least two independent dynamical relations? And so, for example, suppose you have 3 points that depend on your parameter, T, remember I always call the parameter T here. I have 3 points, and one type of dynamical relation might be an orbit collision between points 1 and point 2, and maybe at some other times you have an orbit collision between points 2 and point 3, and for how many parameters T can you have both of these orbit collisions simultaneously? And we expect that to be rare, okay? In the same sense that we expect, that we know that these intersections are small. We expect that there are only to be, say, finitely many parameters unless the points you started with had a persistent orbit relation for the whole family. Okay? But we don't know how to prove this. And I will say we're very far in the dynamical setting. In fact, I'm not sure if there are any cases known, unless there are only 2 points, in which case then have double orbit relation would mean they're both the analog of torsion. They're both finite orbit. Let me just say this. Caution. So I said we really know very little. There is an analog of Silverman specialization, but because there are no inner products, we do not have bounded height, for example, for the parameters where there's at least one relation, orbit relation. So if you're given a family of maps, sorry, again, the slide is so getting busier and busier. If you have a family of maps and you take some collection of geometric points, that is sections for your family, we don't know if the set of parameters where some dynamical relation takes place, for example, a collision between 2 of the points, if the set of parameters where you have a relation will have bounded height in the base. Okay? In families of elliptic curves, that will always have bounded height by applying Silverman specialization to the sort of inner product, the geometric inner product of the points. But here we don't have this. So there is a conjecture that we formulated in a paper some years ago that this really should have bounded height under various hypotheses, but we don't know that. So just saying that, again, we just don't have the structure, we don't have the tools, but inspired by what we know in the setting of a billion varieties, it just feels like it should be true. It just feels like it should be true. I guess in this case, there are some examples known. Of course, the dynamical systems that come from elliptic curves, that come from lattice maps, then certainly we have it. Or when the maps are coming from the multiplicative group. So if you have Chebyshev maps, or you have an isotrivial setting, you have Chebyshev maps, or you have power maps, then the same kind of bounded height statement this type of bounded height statement does hold. There's a paper of Zanier with, oh my gosh, I don't remember. Anyway, so it's known also in that case. So it's an isotrivial case, but it's related to the group structure. So in the dynamical cases that we know are coming from groups, we can say a whole lot more. There's just a lot more structure there. And then the last thing for this busy slide was just one more cautionary remark related to what I was thinking about as I was preparing this talk and reading through the PDF papers on Emmanuel's website, and thinking about this pink Zilber formalism and what it should be. And unfortunately, the axioms break down at step 1 when thinking about what notion of special should mean in dynamical systems. I mean, we have clear candidates of what special means in families of dynamical systems. Things that are pre-periodic or where orbit relations take place. I mean, there are various sort of obvious things that are special in a dynamical sense. But for example, these notions of special that we've come up with are not preserved under intersection, unlike what happens in the setting of abelian varieties. And so even just forget about families. I mean, even for one dynamical system, say a product of maps P1 cross P1, you have one map. You can very easily set up examples of a pre-periodic subvariety or two pre-periodic subvarieties that intersect, but their intersection point is not itself pre-periodic. Okay? So you could even, I could write down an example. Anyway, they're very explicit, it's all the time. So specials are just not preserved under intersection. So we have to throw that out as one of our axioms. So, and then of course, we don't have the extra input of concepts of bi-algebraic, for example. And in the elliptic curve case, you know, the universal covering is this nice transcendental universal covering map, and one can talk about, and abelian variety is the same, or in the moduli space is the same. But in our case, we just don't have that. We don't have these nice transcendental covering maps that we can use to prove things with. So anyways, there's a lot to be done there. I don't know what the formalism should be, but the end statements seem that they all should be true. The corresponding intersection statements, the unlikely intersection statements, we expect them to hold in much more generality. All right, how am I doing on time? Let's see. I started at, what was it, 11:20? It was 20? Great, okay. All right, so I want to spend just a little time. In my abstract, I mentioned I wanted to talk about some of the geometry underlying this statement and how Mirto and I were thinking of it, because the proof was really not arithmetic per se. We were really thinking of it in terms of the complex geometry of this family of elliptic curves. But of course, what did we actually want to prove? I want to prove something that's very formal. I want to prove that, for example, there are no two vectors x and y in this real vector space for which this dots to 0. That is to say, where this thing gives you 0, but unless they're linearly dependent. So no linearly independent real vectors that dot to 0. So that's what I want to prove. So that sounds very formal. What's the geometry there? So here I wrote, I want to ask the question, so some analog of taking these intersection numbers, but for these formal vectors, x and y, and when can they dot to 0? Now the first observation though, if I want to give geometry to this problem, this doesn't make any sense. Like, these are not objects. There is no line bundle associated to this real vector. Okay? So, however, it turns out there may not be a line bundle, but there is an R divisor on this curve B that I was talking about, that the base B, there is a divisor, an R divisor, that is naturally associated to each of these real vectors. And each of these things actually turns out there is some sense of metrizing this R divisor, and there is some interesting complex geometry associated to each of these elements. So I want to spend a few minutes telling you the complex geometry associated to these real points. Okay, so I'm looking now again at the rational points of E over the function field tensored with R. So I'm taking one of these real vectors and I want to give it some geometry. Okay, so what geometry is that? Well, the first, actually, oh, I forgot I had this next, sorry. The first thing was that even forgetting about elliptic surfaces, okay, so forget about the elliptic surface setting, cross this out. I want to say that Mirto and I wanted to study a little bit of the structure of, like, what is a metrized R divisor anyways? I don't have time to give formal definitions, but one thing we realized, that whatever it is the divisor equipped with a collection of subharmonic or plurisubharmonic functions giving rise to metrics at each place of the associated number field, that we could follow the proofs of Galois equidistribution in the setting of abelian varieties or in other projective varieties associated to heights with good properties, we could do the same for R divisors. So just to mention, and bringing it back to the work I mentioned at the very beginning of Emmanuel and sort of some inspiration related to this project, this is, I'm not going to read this out loud, okay? This is a theorem, it's stated in the paper, and I put it on this slide so that you could see that it exists. The theorem, however, just to say what it is in a general setting of, let's say, a projective variety equipped with an R divisor, an ample R divisor, which itself has something called a continuous and nav-fidelic metrization. So there's some notion of metrizing the divisor, like a line bundle, but of course there is no line bundle associated to an R divisor. It satisfies some normalization, and the conclusion is that the Galois orbits of small points are uniformly distributed with respect to some associated measure, exactly the same as they are, this is sort of exact copy of, for example, the theorem in Xinyi Wan's thesis, where he sort of gives this statement for actual line bundles. I mean, here we were just extending it to R divisors. Now, fortunately, we were able to use a lot of the work of Mavraki, who did a lot of the machinery for us in the extending various statements from the line bundles to R divisors. So that was just a remark to say that this is in the background also of what I'm saying, but I wanted to talk about the complex geometry of the objects we're using. And I have a few minutes. So what was the complex geometry associated to these real points? Again, rational points, so E of k tensored with R. So first of all, what's the geometry of the actual points? Remember, I want to do it first in just purely complex analytic language. If you have one of these elliptic surfaces, there is a smooth 1-1 form, in fact, a canonical one, on your surface, at least away from the singular fibers, which has the following properties: that it restricts to be the Haar measure on each of these smooth fibers. Okay, we're working over the complex numbers now. So it restricts to be the Haar measure on each of these fibers, and it's chosen so that it vanishes in the direction of, say, the zero section that I've chosen, or more generally, in the direction of the algebraic curves which correspond to the torsion points. So just from complex geometry, you can build such a thing. So it's Haar measure on the fibers, and it's vanishing along sort of the zero section or in the torsion directions. Okay, this pins it down up to scale. It pins it down uniquely up to scale. And I'm calling it here the Betty form because I think it is associated to the Betty foliation of this family of elliptic curves. I have a question mark here because I wasn't sure who to attribute the sort of study of the Betty coordinates and the Betty foliation in the context of these, in context especially of unlikely intersection properties. So problems. But in any case, let me just say I'm calling it the Betty form because it is exactly sort of the natural 1-1 form that you get from pulling back the standard, in this case dx dy, from the Betty map, as it were. And there's an associated foliation, complex holomorphic foliation, which if you know about the Betty map, which I haven't defined here, those are just the fibers of that Betty map, but they fit together to form a nice foliation of your, at least the open part of your elliptic surface. Okay. So again, so the algebraic leaves are precisely the torsion points, the torsion algebraic curves. Okay. Now, the curvature form for that line bundle that I was mentioning before, so suppose I fix a section P. Okay, the curvature form for that line bundle, at least at some fixed Archimedean place, is nothing but the pullback of this Betty form. Okay. So basically I have this Betty form that lives on the total surface, and remember my section is just a map up into the surface. So you can think of it as, remember that the Betty form is vanishing, in fact, along these red curves, and then I'm just crossing through it with my section. Okay. So that's what the curvature form associated to this thing. And it's actually not hard to prove. that this curvature form vanishes, exactly when P is a leaf of the foliation, which means it's an algebraic leaf of this foliation, so it has to be torsion. That was probably first observed by Manin, but there are a number of proofs now. It's not too hard to prove once you know what to look for. Good. All right, so what I want to say. So that's the Betty foliation, and I have a few minutes. I'm going to get to the picture associated to a real point. Now suppose I have a genuine section, now my point P. Each point P also gives rise to a foliation. Okay? Each section P also gives rise to a foliation. Now what is it? There are two ways to think of it. If you make that your zero section, then this is just the Betty foliation associated to that new zero. Okay? So the green foliation is just a Betty foliation with a different zero, changing your group structure. Or you can take my red foliation, the original foliation, and just add the point P in every fiber. So you just take this family of curves and you just shift them, translate them by P in each fiber. Okay? So each section gives you a foliation. So again, nice geometry in your elliptic surface. Okay, and so then the real points, if I take a vector in this vector space, E of k tensor R, it turns out they also are associated to a foliation. They're also associated to a foliation. Now, so what is this foliation? Here, one just works directly with, so if X is formally a real linear combination of those points, you can just formally take real linear combinations of what are called, the Betty coordinates associated to those original points, and you can define then an associated foliation. Now, one thing to keep in mind, if this is just a real vector and not related to one of these actual sections or some finite extension of K, there's not necessarily any algebraic leaves anymore. This is just some holomorphic foliation of this open surface that may not have any algebraic leaves at all. And you can describe which ones do have algebraic leaves in terms of how they're related to some point when passing to a finite extension of K. So it's just some interesting geometry that these real points really have some complex geometry associated to them. And this is how Mirzo and I were thinking of these points. Because once you have this geometry in mind, you can just as easily talk about, so the analog of this metrized line bundle with its curvature, you still have a holomorphic form, not a holomorphic form, a 1-1 form on the base B that's given by some explicit formula in terms of the generators, the basis for your vector space. So this is just some expression. I just wrote it down so you could see what it looks like. Given a real vector X, so a real linear combination of P's, you can write down whatever this curvature form should be at this particular Archimedean place in terms of the associated curvature forms for the points and the sums of the points. Okay? And so this is just some expression, but it is some nice 1-1 form defined on the base curve. And you can do this, in fact, at any place very formally. And you get ultimately what can be described as sort of this arithmetically or ideally metrized R divisor on the base. I haven't told you how to define the R divisor itself yet. I'm going to ignore that for now. Anyways, the theorem that I had mentioned before, which related arithmetic intersection numbers for rational points over the function field to the corresponding geometric information of regulators. So that theorem that I mentioned reduces, once you have all this structure in place, understanding like equidistribution type results and have all the structure in place, it reduces to the following observation, which can be described purely complex analytically. That the two of these curvature forms coincide if and only if these are exactly the same foliation. Up to this plus or minus. Okay? So it's, in fact, a purely complex analytic statement at the end of the day, that the two curvature forms coincide if and only if the points are basically the same, if and only if they're the same. All right, now I say it's a purely complex analytic statement unfortunately, I don't have a purely complex analytic proof. In fact, the proof was very much inspired by the proofs of the previous unlikely intersection results in this direction. So I am, of course, grateful for learning a lot about sort of transcendence theory input and some computations that had been done in a paper of Corvalla, De Meo, Masser, and Zanier that came out a few years before. There's something that I learned that Lars Kuhne taught me from this paper of André Corvalla and Zanier, this holomorphic anti-holomorphic trick. But really fundamentally, we're relying on a result of Daniel Bertrand that was published in 1989. So in fact, I don't know how to prove this complex analytic statement complex analytically, or at least purely so. We're relying on quite a bit of input. And I'm very interested to know. In fact, I would say I tried quite a while because it seemed super explicit, even in particular examples. Actually, there is one family of examples where we know how to prove this if and only if in explicitly just with complex analysis, working with the Legendre family of elliptic curves with, well, I guess there's not sections, but where sections of some up to some branched cover that have constant x coordinate and those things. There is one setting where we can prove this complex analytically, but with this machinery, we were able to see this equality in general. So it's an independence. So it's the independence of what? So here you input. I'm inputting the coordinates of the points. I'm passing some universal cover, and I'm looking at the coordinates of the given points, the periods associated to the family of elliptic curves, and the statement is and their derivatives. And so it's a sort of a list of these holomorphic functions and saying that they are independent over something.
Functional transcendence.
Thank you. Functional transcendence of these holomorphic functions. It's involving the periods and starting with some algebraic sections. Yes. So I could give you the explicit statement, but I'm not an expert in this area, so for me it was this miracle black box that existed. I thought, thank goodness, he has exactly the statement that we needed for this case. So it really felt like magic to me. So anyway, so we do in fact use all this. But okay, I have to finish. The last slide, which I'm not even going to show you, I guess, was to describe dynamical analogs of this. So there's a question of, in a much more general dynamical context, we don't know this type of statement, this just purely complex analytic equivalence of the curvature forms and whether you can extract orbit relations, algebraic relations between the points just from the complex analytic input, and that's still open in the complex case. So I'll stop here.
Any questions or comments?
What is the answer to the question at the bottom?
Oh, yeah, right. So the answer turns out to be if and only if x and y are linearly dependent. Yeah, that's it. Yeah, and that's the only possibility. Just linear dependence.
Could we see the last one?
Oh, the dynamical one? Yeah. So just to show you that this was the question. There's what I was formulating here, and I have a picture in the background, is when you have a family of dynamical systems, there's an analog of what I called the Betty form, which is still over here. It's a dynamical current, which is anyways, an important object in complex dynamics and satisfies similar properties. And then the question is, when you have a family of maps and say two sections, if just this purely complex analytic input coincide, can you conclude an orbit relation? So I don't have time to give all the definitions, but I'm happy to tell them to you after.
Well, thank you again.